So good afternoon, everyone. Welcome to our seed funding webinar. My name is Chandrabhan Singh Kushwaha, and I will be your chair today. We are here to explore the AI RSTO project, which focuses on AI-driven inverse design for enhanced photonics. This work is tracking a major challenge: how to design complex waveguides for things like quantum technology and sensing without the slow, traditional trial and error process. To present this, we have a fantastic duo from the University of Glasgow. We have Dr. Natale Pruthi, a research associate at University of Glasgow. His expertise lies in integrated photonics and nonlinear device engineering, with a specific focus on low loss platform and fabrication aware modeling. Joining him is Dr. Naveen Kumar, a postdoctoral researcher with Glasgow University's Deep Nano Group. Naveen brings extensive experience in semiconductor devices, from solar cells to quantum dots, and he is currently focused on analytical models for chemical and biological sensors. They will be co-presenting this progress on using neural networks to map desired optical outputs directly to optimized designs. As we also progress through the seminar, we will have the question answers at the end. You are welcome to type your questions in the chat as we go, or if you prefer, you can raise your hands during the question answer to ask your question via voice as well as video. So Natale and Naveen, the floor is yours.
Thanks a lot for the introduction, Chandrabhan. Yeah. Okay. So yes, we are. So yeah, my name is Natale, and we work at the University of Glasgow in photonic integrated devices. And with this project, we are aiming on using AI to help us with the design of such devices, and particularly focused on the nonlinear applications, so integrated nonlinear photonics. So before going into the details of the design, the AI-assisted design, I wanted to start with why we do nonlinear photonics. And the reality is that there are plenty of applications. I'm just showing you 3 applications here. And the core of nonlinear photonics is that you take a signal with just having one wavelength or a specific wavelength band, and you convert this into signal at different wavelengths, different frequencies. And you can use these properties, for instance, in quantum technologies, where you can generate photon pairs that are entangled with each other, which are used for quantum communication computing. You can use this to generate broad spectra, light with broad spectra, that is very useful for metrology applications. So you can think of optical frequency standards, so quantum clocks in the optical domain, and which can also be used for GPS-free navigation. And further, another example here, you can use it for signal processing. So for instance, you can do what's called parametric conversion, where you use a strong pump signal and use this to amplify your desired signal, and you're generating another one at a different wavelength. That's, for instance, it's easier to sense. This is just, again, a small subset of application, but the point is that all of these requires that we generate light with a very specific spectral profile, and particularly we want to do it on a compact and scalable chip. So this is the typical setup we have. We have an input signal, which in this case I represent as just a single frequency signal, and we want a specific signal with a desired spectral profile. We can see here on the right. And in our case, we want to do this with an integrated nonlinear system. So you can see here just a sketch of a waveguide paired with a ring resonator. For people not being in the photonic community, you can see this just as the wire or a transmission line, and then a component. And then the thing is that these photonic circuits can manipulate lights on the chip in the same way electronic circuit manipulates electrical signal. And the key aspect here is the interaction between the light and the materials making the waveguide or the devices this results in a nonlinear effect that we can exploit to generate the desired output. And ultimately, when we do the design, all we care about is the geometry of this chip. If we get that right, so that's the way we control how the light interacts with the material, and this way we can control the output spectra of the light. So more specifically, you can see here that we work with what we call the cross-section of the waveguide. That's basically just the waveguide dimensions, but also the material that the waveguide is made of. We can have a uniform material waveguide, where the core is just made from a single material, but you can also combine different materials together, which further complicate the design problem, as you'll see. And based on this cross-section, you have an optical mode, and that again shows you how it interacts with a different material. And then we can use resonant cavities to enhance the interaction of the light with the material, so to further improve the nonlinear phenomenon. And what is important to understand here is that very small changes in the geometry can have very big impact in the output. So we need to be very careful with the design. So what we do in general is that we have our set of variables. So we have our input signals, and we want to design the integrated circuit. And of this circuit, we have different parameters such as the waveguide cross-sections, or even the waveguide profile, so how the cross-section varies, if it varies at all, along the direction of propagation of the light. And in this case, we also have a resonator with its profile and its size. But further to this, we can have also different fabrication non-idealities, so we can have slanted sidewalls or roughness or rounded edges. All of these will play an effect in our modeling. And the way we typically do this design is just a forward model. We do the simulations of the optical modes, and then we calculate the output. But this is really not scalable, because even if you want to change slightly the application, so we want to change the output spectral profile, you have to redo everything from scratch. So this is clearly not scalable in the classical way. And I would say it's the perfect example of how AI can help us with the design of these circuits. So to go into the details of this, I'm going to leave the floor to my colleague Naveen here.
Hello, am I audible enough, right? Okay. So moving on, assuming that we are working with waveguides with different parameter space, and for us, it's actually the type of material we are going to use, its physical dimensions. That's it. That seems like a very small set, but as we move forward, we will know that how complex this can get. So what we actually do for the starting and making our data set, we use those waveguides and we do numerical mode simulations. And those mode simulations will give us, based on the physical dimensions and materials, it will give us at least 3 main parameters that we have calculated later on. Those are the effective indices of those materials as in combined one, and you will get the group index, and you can actually get the effective area of the modes. What modes that Nathalie has shown just now, that optical mode, how the mode looks like, its area on it. But these area are calculated even on numerical as a based on approximated equations, depending on what type of meshing we have. So after generating this data, what we actually used, we used very simple MLP forward neural networks with, I think, just 3 hidden layers with 128 neural networks. And we generated those data. And for an example, I will show you, just take as a waveguide here, we have width, thickness, and the lambda as a variable parameter. And this is a very simple waveguide, but now assume like this: if you have a simple waveguide and you overlap it with different materials, such as, say, other than silicon nitride, what if you have titanium oxide? What if you have aluminum or alumina? And you will have, let's just say, if you take just 3 layers of these waveguides, you will have 3 to the power 3. Now, if you take 6 layers, 6 to the power 3. So your sample space is actually going exponential to the power of n, depending the number of layers that we are taking. So it's gonna explode depending what type of applications we want at the end. So that's why we are trying to first simplify the data set by making it with a normal neural network. So here, what I'm showing is the TE-based mode, the transverse electric field. That's the fundamental mode. And similar to these modes, there can be 100 or 200, depending on the dimensions, there can be 100, 200 modes. And for every single mode, those extracted values are different. So those becomes multimodal waveguides. So for the fundamental mode, if I take these values with variability and I made a surrogate model with simple MLP, matching these are quite easy because they are not complex. But this single mode now, and this is the one of the parameters that's the effective index with respect to the wavelength. And the solid lines you are seeing are the surrogate model that we have generated with, and the simulations are the symbols, and they are matching perfectly fine. I have taken two more parameters, that's the group index and the effective area. Those are working fine. But if you actually look at the error is higher for the, as I've mentioned before, it's higher for the effective area because it's calculating based on the integration, how the mode fields look like. So this it's not much, it's 0.1%, and it can be worked with later on. Okay, so this was just one of the waveguides. And now think that if we have that simple waveguide and we have 2, 3, 4 geometries, those are the meta waveguides. We have done that as well, but for those we are getting around 2% error. And that can be solved if we actually make the neural network more complex. But remember, these are done for single mode, not multi-modes. For multi-modes, we have to use, let's say, regression-based models later on as well, because we don't know what type, or we can actually manually input changing the neural networks per hidden layer and then get the output, or we can do a regression to get the error at the end at the lower value. So now we got these values from the neural networks. Now our task is, if we have those waveguides and if you put some signal into it, how it actually behaves. And for that, these are for different modes. That's for TM modes. We are getting very same values. For that, we actually use the generalized nonlinear Schrodinger equation. Schrodinger equation looks simple, but for this one, even I don't have a photonics background, it's too much complex. Okay, so the red looking terms are very highly nonlinear based on the propagation constants, all depending on the material properties. The blue one is the Kerr nonlinearity and the Raman nonlinearity. Those are the material dependent. We cannot control or we cannot extract them. They are fabrication or the process-based properties. But what we actually calculated are the top 3 values, that the mode dispersion, propagation constant, the effective index, what we are controlling right now. And that we can predict, but the below blue and the green one, we cannot predict, and we cannot even calculate it via simulations unless we move on to DFTs. Okay, so we have these values and we have to first make an analytical model out of it. And for that, what we have actually done, we have used a very simplistic model or the method called the split step Fourier method. And what we actually did here, assume that you have a pulse, and we have seen from the equations that those equations based on some linear functions and nonlinear functions, and those some are time dependent, some are frequency dependent. So what we did, assume you put an input pulse to a medium and you get some spectrum with respect to time, location, and depending on the frequencies. We take those values and we separate them into one with, we actually solve it first with keeping nonlinearity as 0 and linear terms, and other one is nonlinearity as having some certain value and the linear terms as 0. It means just separate them and then concatenate them at the end. So after doing this, we actually do that same thing with respect to the length of the propagation. And that can be done with FFT and IRFT based on if you have a time domain and the frequency domain. And at the end, we can see from the spectrum if we are getting some pulse with respect to frequencies or with respect to time, where we can actually calculate the nonlinearity factor or the dispersion effect. So using this step, we get some really good results and they actually match the standards. So assume that you have a sec pulse here, and due to some material properties, if the same pulse propagate along a distance, it got distorted. It looked like some random peaks to me. Okay, but if you actually look at the power spectral density with respect to the frequencies, those get spreaded along the frequency range, and the values are quite high because these are normalized values. Okay, so after having these values, if I have to see, let's just say if I make my waveguide look like this, and I want to see, okay, where those pulses are going around. So those are along the distance. Those looks like something like this. The left curve is the distance with respect to time and how the pulse is evolving in the dB scale, and the same with respect to the frequency, how the pulse is evolving. It means I can see that it is spreading quite a lot, and these are based on the nonlinearity effects. This is quite good, but here's the fun fact. It means till now, whatever GNLC has been implemented are done assuming that you have a same width across the length. But what we will be working on is what if you want to change the widths. It means if you take a GNLC, if you solve it for a very short slice, you need to actually repeat it over the number of slices with the variation in the widths. It means your material properties, that's the beta propagation constants, or the material properties does not remains the same. They are changing with widths along the slices. So we will have to repeat the third step again and again, where the delta Z is changing with delta W as well. So that we are currently working on right now. So for the simple explanation, we actually took the same values, but excluding the nonlinear parts, we actually tried generating a very simple pin-based GNLC, and this does not include the nonlinear part, but only the linear part. And for the first graph, we are just showing how the energy is actually changing along the propagation distance. That matches quite fine. But those energies, what we are actually lacking, we cannot match it when we are moving away from the frequencies, the higher frequencies, and those frequencies are coming from the nonlinear factor of the beta 2 and beta 3 values. So this is done on a very basic CPU, around 3,000, 4,000 epochs, not much. We need to change it a little bit more with slower learning rate and for a longer period of time. So this works fine, but we will extend that pin to conditional GAN later on. Why? Because we need to train those output values based on the input parameters every single time, and we don't want that. We want one-shot method where the CGAN can provide us a particular output, which we can use as an inverse design method to actually approximate my geometry for a specified, let's say, applications. Yeah. So these are, they are not that good enough, but we are working on it. Okay, thank you.
Thank you.